Welcome back. It's Noan and Renard. Talking again today with the UCL IXN HoloRepository project in collaboration with ToukanLabs. Today we're going to be talking about organ segmentation, the first major step in our project. So, first of all, we got to ask ourselves the question, why do we need to do organ segmentation? So, organ segmentation, in our case for the eye of OCT images, is an essential step for data analysis for many areas of biomedical research. So, in our case, it allows to clearly identify the regions of the eye that are necessary for more accurate diagnosis. So, for example, it can help with earlier detection of ganglion cell loss, allows for the comparison of retinal thickness, it gives volumetric measurements in the whole scan, and allows for calculation of similarities between the left and the right eye. So how's this done normally? So traditionally, this task is performed manually, and in the case of OCT images, it's done by delineating the outlines of different layers. So the problem with this is that this procedure requires great attention to detail and expertise in human anatomy and the imaging modality. Moreover, it's highly repetitive as a task and time consuming. As a result, manual segmentation is very difficult even for experts, which still is prone to human error and bias, making it all in all very inefficient. The other techniques to try and circumvent this and try and do it automatically are detailed in a paper which is a meta review of algorithms for OCT segmentations, published in the J Medical Signal Sense Journal in 2013. And it documents many of the most effective techniques for this. Segmenting algorithms using graph search, FVMs, 3D graph search, Siemens clustering. However, the problems it details is that OCT images suffer from the intrinsic speckle noise problem, which decreases the image quality and complicates the image analysis tremendously. Furthermore, this is combined with the inherent messy nature of OCT images, and they are prone to many different problems, such as potential fluid and blood vessels being shown in the images. So, the paper concluded that no typical segmentation method exists that can be expected to work equally well for all tasks, quite limiting. However, in 2015, there was a breakthrough paper. Title of the paper is Convolutional Networks for Biomedical Image Segmentation, which is exactly what we're talking about. So, what is this? So, this Swedish research group created a U-shaped convolutional neural network architecture, which is very, very effective at segmenting images for medical purposes. So the main idea of it is to supplement a usual contracting network by successive layers, where pooling operations are used and are replaced by upsampling operators. As a result, these layers increase the resolution of the output. And on top of that, a successful convolution layer can then learn to assemble a precise output based on this formation, helping us accurately segment medical images, which is exactly what we need. So, with this breakthrough, what do we need for this to apply to our project? So ideally, we'd like a machine learning model which is highly performant, such as one based on the UNet, that has a publicly available dataset, because due to COVID and many other limitations for project, we don't have access to our own proprietary datasets, and have a pre-trained model available, as we don't have the computing capabilities to train our own machine learning model. After lots of research and testing, I found a network called ReLayNet, um, with the link down below. Um, and this fulfills all the problems we had, and with great results. So luckily for us, it comes with a pre-trained model. It uses an open dataset, and most of all, it's state of the art. It has excellent results. But, its results are in agreement with the ground truth images from the experts. It's great at finding edge cases with fluid detections, unlike similar models, and it fits all the limitations we put ourselves through. However, there are some problems with this. It was built in 2017, and used the PyTorch 0.3 machine learning framework, which didn't even exist on Windows at the time, which is the model I'm using. The pre-processing use is undocumented, because they used a custom data loader for their data, converting it to an H5 data structure, and the GitHub code structure is different than the one the pre-trained model used, meaning that it doesn't work out of the box. So how do I go about and fix this? So um, as we're using the most up-to-date version of PyTorch, there are many manual methods that had to be created to allow for these backward compatibility fixes. So adding methods that the machine learning model depends on to work. Moreover, we changed the data entry to the dataset it was using, which is the Duke dataset, which uses .mat files. And there's a lot of pre-processing, and the data entry was changed for it to be compatible with the model. And finally, we had to revamp the structure of this pre-trained model in order for it to work. So the results, after a lot of pre-processing, are as such very accurate delimitation of the different layers of our OCT image here. It has to be rotated, scaled to fit the CNN architecture, but it works really well. So where do we go from here? So we think that with more noise removal, more pre-processing, we can increase the accuracy of our results even further. The next step on the project is creating a 3D model out of this 2D segmented image in the GLTF format so that it's compatible with the HoloRepository. As a result, we have the inherent problem that a 2D image is missing another dimension of data. So we're going to have to go through a lot of different methods on how we're going to try to circumvent this. And some photos here are some of the research that's been done so far. So on different meshing algorithms, different box detection algorithms, etc. The next video will be on creating this 3D model and how we've gone about doing that.